Hi everyone. So we are going to look at another lecture on our course EC303 Applied Electromagnetic Theory. So in this lecture we are going to see, or we are continuing with our module number 5 only, and in this lecture we are going to see some of the matching techniques. So we have seen in our previous lectures that if you want to have maximum power transfer, then you should have the input impedance, or rather the load impedance should be equal to the characteristic impedance. So if this can be achieved, then you have the maximum power transfer, but it might not be able to achieve in all the cases. So we need to develop some methods through which we will be able to achieve this, and these are called as matching techniques. The first matching technique is called as quarter wave transformer. Okay, so this is the first matching technique that we are going to see. So let us consider a transmission line. You have a generator, you have a transmission line with impedance Z0, and then it is connected to a load with some load impedance ZL. Okay. Now, if you want to have the maximum power transfer, ideal situation is you should have ZL equal to Z0. Now, the load might not be, the impedance of the load might not be in our hands. So it can be possible that the load will be some antenna where you might not have any control over how the impedance looks like. So what can we do to make sure that if I look from here, the impedance I see is equal to Z0, because this is the where you are connecting the load. So you don't want this to be Z0, but if I look at from this juncture, the input impedance that I see should be Z0. That means then the transmission line sees the load impedance as characteristic impedance. So what can I do? So you cannot change the ZL value, because ZL value is completely out of our control. So what we can do is the following. This is our normal generator. This is our transmission line. Now at that juncture I can connect a different transmission line, because you can always connect a new transmission line here, okay, and I connect the same ZL load. Okay, so this is another transmission line which I am connecting, so that when I look from here, I see Zn is equal to Z0. Okay. So now the question is, what should be the length of this transmission line? Okay. And what should be the characteristic impedance, or I say Z0 dash. So this is Z0, the original transmission line. I have a new transmission line I have connected, which when connected with the original load, and if I look it from the old transmission line, I see the characteristic impedance. So what should be the characteristic impedance and length of the transmission line, so that you will have a match condition. So to analyze this, let's go back to our input impedance relation. So this is Zin is equal to Z0 ZL plus JZ0 tan beta L by Z0 plus J ZL tan beta. Okay. So let's say my L value is equal to lambda by 4. So my beta L value, which is electrical length, is 2 pi by lambda into lambda by 4, that is lambda by 2. So my Z in, I can write it as Z0 into ZL plus J Z0 tan, so this is pi by 2, tan pi by 2 divided by Z0 plus J ZL tan pi by 2. Okay. Now you know tan pi by 2 is infinity, so I cannot directly substitute here. So I can take out tan pi by 2, so I can write that as Z0 into ZL by tan pi by 2 plus J Z0 by Z0 by tan pi by 2 plus J ZL multiplied by, actually you have tan pi by 2 at the outside because you have taken tan pi by 2 out. Okay. So this will get cancelled. Okay. Now when I put a limit for this one, when I put a limit for this one, that is as tan pi by 2 tends to infinity, you have this will be equal to, because this value will become 0, because tan pi by 2 infinity, this value will also become 0. So you will have Z0 square divided by ZL. Okay. So your Z in is now equal to Z0 square by ZL. So you want to find the new characteristic impedance, right? So our Z0 square, Z0 is actually Z0 dash, which is this one. So that is what we want to find. Okay. And the input impedance is equal to Z0, because that we have mentioned. So this is our final condition. The input impedance should be equal to the characteristic impedance of the transmission line, which is this. Okay. So if I substitute this here, I will get Z0 is equal to Z0 dash square divided by ZL, implies the value of Z0 dash is equal to root over Z0 ZL. And this is the condition in which you will have the matched impedance. So a quarter wave transformer will have a transmission line of length lambda by 4. That's why it is quarter wave transformer, because it is quarter of the wavelength, and characteristic impedance of root over Z0 ZL, where Z0 is the characteristic impedance of original transmission line and ZL is the load impedance. Okay. So now if I make in this figure, if I have L equal to lambda by 4, Z0 dash is equal to root over Z0 ZL, then I will have my Z in is equal to Z0. So the generator will see a load impedance of Z0, which is a match condition. So in this match condition, there will not be any reflected wave from the point, let's say this is AB point, from this AB point. okay, and you will have maximum power transfer. So this is called as the quarter wave transformer, and it is used to match any load condition. Okay. So if you take an example, just to take some random values, let's say your Z0 value, the original transmission line characteristic impedance is 75 ohm, and your load impedance is, let's say, 120 ohm. Then your new transmission line will have the characteristic impedance root over 75 into 120, which is approximately around 95 ohm, with L equal to lambda by 4, the length of the transmission line. So thus you can design a transmission line to match the transmission line which you have already connected, and you will have the maximum power transfer. So this is one of the matching technique. Now the other matching technique involves Smith chart. So the second matching technique is called as single stub tuner or single stub matching. Okay. So stub is something you connect in parallel, that is called as a stub. So if you are, this is the transmission line, okay, and you have some generator here, and it is connected to some load. Okay. Now let's say I want to match this load to the transmission line with characteristic impedance. What I will do is, at some point A in the transmission line, so basically this transmission line extends all the way. Okay. So I am just drawing it as a single line instead of drawing it as a block line. I just draw it as a single line. So this is again the transmission line, so that the figure will not be messy. Okay. So what I can do is, I will connect a parallel transmission line like this, okay, which has some kind of a load, and usually we connect a short circuited transmission line. Okay. So you see that these two are parallel, this and this are in parallel. And so basically your transmission line should have some distance. So let's say this distance is D. So let's say this point is A and B, and there is some distance from the load also. Let's say that is L. Okay. And this is called as short circuited stub. It can also be open circuited, but we will not use open circuited stub because it will give out many varied frequencies. So like it radiates some energy at very high frequency. So that is why we prefer always short circuited stub. Okay. So what we want to go and find is what should be L, what should be D, what should be the characteristic or admittance or impedance of the short circuited stub. So I say Z of short circuited stub. This much we want to find, where L is actually the, or let me write it clearly, L is the distance from ZL to the point where the stub is connected. D is equal to the length of the stub. And you should note that all these are transmission lines. So this, the short circuited stub is also a transmission line. Along with this is also a transmission line. Okay, so everything is transmission line, but now you have two parallel loads. Okay, so first load is this and the second load is this. Okay, so you have two parallel loads connected in parallel to a transmission line, so that if you look at from here at this point, the input impedance Z in is equal to Z0. So that is this point. So this is the concept of short circuited stub. Now let's look into deeper and see how we can make that happen, in which the input impedance, if you look from A to B, is equal to Z0. Okay, so let me draw that once again. This is a transmission line, and you have a load. This is saddle, and you have the short circuited stub. Which is connected to a short circuit. This is L, this is D, these are points N. Okay. Now, whenever you have something connected in parallel, you always deal with admittance. So, any parallel connections, any parallel impedance means you deal with admittance, because for parallel connections, the net admittance is the sum of individual admittance. Okay. So if this line has an admittance, let's say Y1, and this line has an admittance Y2, the net admittance, if you look at from here, Y in will be Y1 plus Y2. Okay. So you can have this as normalized admittance. So the normalized admittance at the point AB should be equal to the sum of admittance of Y1 and Y2. Now what you want to have? You want to have at this point AB, the input impedance should be equal to Z0 at AB, or the normalized input impedance should be 1, or the normalized admittance is equal to 1 by Z bar in, that is equal to 1. So at the point AB, you should have Y bar in is equal to 1. So if this condition is met at AB, then you say that it is matched. Okay. So this transmission line has input impedance, characteristic impedance Z0. So what can we do? So the trick is like this. Now first one, find the length L such that at AB Y1, or the admittance Y1 is equal to 1 plus some reactance. For B can be positive or negative. Okay. Second, find the length such that at AB y2 is equal to minus JB. Okay. So y1 will be 1, it should be there, plus or minus JB. So you can plus JB or minus JB, whichever is possible. So you can write or y1 bar is equal to 1 minus JB. Or in the second case, can be y2 bar is equal to plus JB. So if you are finding 1 minus JB, you should find plus JB for y2 bar. If you are finding 1 plus JB for y1 bar, you should find minus JB for y2 bar. So implies the y-in at AB is equal to y1 bar plus y2 bar, that is 1 plus JB minus JB, that is equal to 1. So y1 bar is equal to 1 means it is matched, because that was our condition. So basically this problem involves 1, finding L, which is the distance, 2, finding D, which is the distance of or the length of the stub. If you can find these two, then you are done, because you know that this load here, so this is another load which is a short circuit, because you don't want to design for anything here, because short circuit load means your ZL dash is equal to 0. So everything is there. Now finding this numerically is very tedious process. So instead we are going to use Smith chart. So this is the Smith chart, and we are going to first see how can we do this. Okay. Okay. So let's illustrate the step. The first step, as always, is mark the impedance ZL or ZL bar, the normalized impedance. Second, draw a constant VSWR circle with 00 as sender and ZL bar as radius. Okay. Next, you draw the resistance circle R equal to 1, because you see that at AB for length L, your y in should be is equal to 1 plus JB. So this one indicates the R should be equal to 1. Okay. So you can also mark YL bar also. Okay. So that's why we are going to draw the resistance circle R equal to 1. Then find the intersection of R equal to 1 and constant VSWR circle. Okay, so there will be 2 points because circle will intersect at 2 points. Fine. Okay, now let's do one thing. Let's mark all these things before we proceed. So, for example, let's take SZL is equal to 40 plus J 30 ohm and Z0 is equal to 100 ohm. And you should match for this load impedance. So, my ZL bar is equal to 0.4 plus 0.3 J. Fine. So, let's mark these points, and so first one you need to mark at 0.4 plus 0.3 J. So, let's look at where is 0.4, which is this circle, and 0.3 is somewhere here. Okay. So, I need to draw a circle, center here at origin. So, let me try to draw this freehand. Okay, 0.3 and 0.4, am I right? Yeah. I hope it is at the center. Okay. So, you have drawn the constant VSWR circle, and this is ZL bar. Next, you find the YL bar. So, let me first draw the straight line from the point O to ZL bar. Okay. So, for finding YL bar, it is a diagonally opposite point. So, it is easy to draw from, in my case, it is easy to draw from ZL bar to O to the point. Now, let me extend that. Okay. And this point is YL bar. Okay. Next, as per the step, you need to draw the step number 3, draw the resistance circle R equal to 1. So, R equal to 1 circle means the circle which is represented as R equal to 1. So this is R equal to 1 circle. So that is our R equal to 1 circle. Now you find the intersection of r equal to 1 circle and the constant VSWR circle. Let me mark all these points. So this is O, this is A, this is B. So intersection of the circle r equal to 1 and circle is somewhere here. Similarly, a similar intersection will occur somewhere here. Okay. Fine. So this is P and this is Q. Okay. Now you can draw a straight line from 0, 0 to Q, and you can just extend it. Or let me draw it correctly to Q and extend. Similarly, you can draw a straight line from O to P and extend it. Now at O and Q you have 2 points which has r equal to 1 at transmission line. So here also r equal to 1 at transmission line. So in the transmission line, so let me show this diagram. So the Smith chart points P and Q is these 2 points. So that is in the transmission line. So if you move L distance from the load impedance, you will get the point P. So we want to find out what is L. So this from point B to Q, if you move this distance, and that should be in the it should be in the clockwise direction. If you move from the point YL to Q towards the generator, you will get the point at AB. So towards generator means actually you want to move in counterclockwise direction. So this you move in this direction, okay. You will get the point in the transmission line of distance L. Actually we will get 2 distances because it is intersecting at 2 different points. So this is LA, and then there is another point P here. So if you move from B in the counterclockwise direction to P, you will get the next length LB. So basically you will get 2 lengths, because in your transmission line there will be multiple points in which you will have resistance is equal to 1. Okay, so you can connect the stub at any point. For example, in this transmission line there might be some point here which might have r equal to 1. So that's why, so this is LA and this is LB. So you can connect the stub either at A, B or at MN. Is also possible. So that's why you are getting 2 distances. Okay. Now you find the distance LA. So to find the distance LA, you should be done in terms of lambda. Okay. So if you look at here, the wavelength towards generator, which is this, is around 0.33 lambda, and here it is around 0.3, sorry, so this is around 0.303 lambda, and this is around 0.335 lambda. Okay, so your LA is equal to 0.335 lambda minus 0.303 lambda. Make sure you take the distance only in this part, because this is the wavelength towards generator. Okay, so your LA distance is equal to 0.303 minus 0.35, which I can write approximately as 0.035 lambda. So your stub should be connected at a distance of 0.35 lambda from the load, or if you measure this distance, so this is approximately 0.165 lambda. Okay, so you need to measure LB, which means from 0.03 lambda you need to traverse all the way, let me mark in different color, you need to traverse all the way up here. Okay, so if you traverse up to here, so you need to traverse all the way, sorry for my freehand drawing, up to here. Fine. If you had traversed up to here from this point to here, then this will be lambda by 2, because you know that lambda by 2 is 180 degree. Sorry, lambda by 4, because you know that lambda by 4 is 180 degree. Okay, so at this point here you have traversed 0.25 lambda. Okay, and then the point here, so this is traversed 0.25 lambda, and the point, if you look at here, this is 0.055 lambda. So the difference between these 2 points is around 0.11 lambda. Okay, so the total distance you have traversed for lambda LB is equal to 0.25 lambda plus 0.11 lambda is equal to 0.36 lambda. So you can connect the stub either at distance LA is equal to 0.035 lambda or at distance LB is equal to 0.36 lambda. Okay, so if you let me go back, so you can have LA is equal to 0.033 lambda or LB is equal to 0.36 lambda. In either distance you can connect the stub. Okay, now you have connected the stub. you found out how much distance it should be. Now you want to find out what should be the stub impedance or admittance and how much distance the stub should be connected so that it will cancel out the reflections. Okay, fine. So let us write down these steps. Okay, the fifth step, after we find the intersection of R1 and constant VSWR circle, then find the distance between YL bar and the points of intersection. So we labeled it as LA and LB. So we will have two different points. Okay. So this is the points in transmission line at which the stub needs to be connected. Fine. Next step is to find the distance dA or dB and the impedance of the stub. Okay. For that one, you see the stub impedance or stub admittance is equal to minus JB or plus JB. Okay. So this means that this is purely reactance. There is no resistance. Okay. And in our Smith chart, we have the outermost circle have R equal to 0, which means purely reactance. The outermost circle is purely reactance, because if you remember, the outermost circle have the center at R by R plus 1 comma 0 and radius is equal to 1 by R plus 1. Okay. Fine. So when R equal to 0 implies center is 0 comma 0 and the radius is equal to 1, which is the outermost circle. Okay. So from the point where the intersection happened, we find out which is the reactant circle which touches the R equal to 1 circle. Okay. So let's do that. So this is the point B. If you draw this circle, basically this is the constant reactant circle which is passing through the point Q, and the impedance here is minus 1.1 J. Okay. And in a similar manner, this is the point P in which you have the stub connected, and if you draw a line like this, which is plus 1.1 J, so this circle. Okay. So that is your admittance Y2 or the admittance of the stub. So this is the both by 2. So if you look at the Smith chart, so the point PQ is on the transmission line. Now in the same point you should have minus YB or plus YB. So you find out the circle which has only constant reactance. Okay. So this point, at this point you will have, because it is intersecting with the outermost circle, which means the resistance value is 0, you will have only reactance. So that is the point in which you will have the resistance is equal to 0, and that is the impedance of the or admittance of your stub. Now you want to find out how much distance your stub should be there, or what is the length of the stub. Now you know that the stub is terminated with a short circuit. So the load in the stub is short circuit, and we also know that short circuit is this point. Let me draw with a different color. So this is the point of PSC or short circuit. Okay. So to find the distance dA, what you want to do is basically, so this is this, let me draw it a bit more up. Okay. So now you are at the point PQ and you need to traverse towards the load to find the distance to the short circuit. This is towards load ZL dash, because now you are in point PQ and you want to traverse towards the load to find ZL dash. Okay, and traveling so this is the point PSC and you need to traverse towards the generator. So this is point PSC, you want to traverse towards the generator here. Okay, so let's draw that also. So this is PSC and this is PSC and this is the point of your AB. So either you can go like this, so from short circuit you traverse towards the point here, so this is DA, and you can also know that there is another point here at here, so you need to traverse another distance here. So this is dB, and you can find out the lambda. So this is, here you see this lambda is 0.25 and you see the lambda here towards generator is 0.37 approx. So the distance dA is equal to 0.37 minus 0.25 lambda, both are in lambda. This is equal to 0.12 lambda, and this point is at 0.13 lambda. Okay, but if you traverse till here it is 0.25 lambda, and then you traverse again at 0.13, so the total length dB is equal to 0.25 lambda plus 0.13 lambda, it is 0.38 lambda. Okay, so what I did was, this is 0.25 lambda. When you traverse lambda by 4, when you reach here you have traversed 0.25 lambda, because 180 degrees 0.25 lambda, and then again you traverse 0.13 lambda. So total you traversed from the short circuit point PSC is 0.25 plus 0.13, that is 0.38. Okay. So let's write the steps. Okay. So find the reactant circle which passes through the intersection of r equal to 1 and constant VSWR circle. Okay. Then you extend this reactance circle to the outermost circle, and this reactance circle is equal to the reactance of the stub, and you will get two reactances, one at upper half and two at lower half. Okay. So this is the reactance of the stub Y2 bar. Next, from PSC, the short circuit point, measure the distance to the reactance circle in terms of wavelength lambda. So that will give you dA and dB. Okay. So this is how you will do a single step matching. Now this is a bit of a tedious procedure, but if you try many examples, then you will be able to understand this. Okay. So I think we will stop it here. So this is almost at the end of module number 5, where we did the single step matching. There is a small topic which we will discuss in the class. Okay. So thank you all. Thank you for listening.